Compress a vision transformer and you face a choice. Two families of tricks do the job. Token compression merges redundant tokens, fewer tokens, same architecture. Structural pruning thins the network, same tokens, narrower architecture. Both cut compute. Both look free at first, push them hard though, and they diverge violently. At the same compute budget, one of them collapses, accuracy nearly halved, while the other barely budges. A team at the Singapore University of Technology and Design built the first head-to-head benchmark and found a clean recipe that gets the best of both. The benchmark is ruthless. Three methods in the token camp: TOMI, which merges similar tokens, and ALGM and CTS, which are segmentation aware. One in the pruning camp, NVT, which thins the architecture to a latency target. And the team's own stack, prune then merge, a moderate NVT prune with moderate TOMI on top. Everything runs on a segmenter-style VIT-T with a DediB backbone, ImageNet pre-trained. Compression is applied to the encoder only. The decoder is untouched. And crucially, every method is compared at matched flops, because a token ratio and a pruning ratio are not the same thing. Two segmentation datasets anchor the study: ADE 20,000, indoor scenes, and cityscapes, street driving. For each, a corrupted twin, 16 corruption types, 5 severities each, 80 variants per image. That yields 2 scores: clean MIOU on the original images, and noise MIOU averaged over all the corruption variants. Matched flops is the common axis. FPS is measured separately on a single RTX A6000. The headline question is simple. At 3.7 times compute reduction, what survives? The diagnosis lives in section 4.3. Aggressive token merging causes feature dimensional collapse. Measure the normalized effective rank of the token features. For TOMI, it drops sharply. For ALGM and CTS, it drops gradually. For NVT, it stays flat. That makes sense. Token compression blurs away spatial positions. Merged tokens lose their place. Pruning keeps the full spatial grid intact, just with fewer channels per position. The collapse is not a mystery. When you merge tokens too hard, the feature space loses the dimensions it needs to tell things apart. First result, the collapse. On ADE 20,000, at a matched 3.7 times flops reduction, TOMI crashes. Baseline is 47.22 clean MIOU. TOMI at the aggressive budget falls to 23.94, nearly half. Its noise score collapses from 35.58 to 16.86. Meanwhile, NVT-S, structural pruning, at the same 3.8 times budget, holds 45.30 clean and 32.86 noise. Same compute cut. One method halves. The other barely dips. Second result, the recipe. The prune then merge stack takes a moderate NVT prune and layers moderate TOMI on top. On ADE 20,000, it reaches 45.71 clean and 34.33 noise at 3.7 times, beating NVT-S alone and beating every token method. It works precisely where the dichotomy predicts. The two levers have complementary failure modes, so stacking them covers each other. One deployment caveat: FLOPS and wall clock speed are not the same. NVT-S cuts FLOPS 3.8 times, but delivers only a 2.4 times FPS speedup. Before you pick a lever, measure latency. The visual tells the same story. Push token compression hard and the feature map blurs and collapses. Distinct regions melt into a haze. The model can no longer tell a chair from a wall. Keep the spatial grid, prune the width instead, and every position stays sharp and distinct. The architecture gets smaller, but the map keeps its structure. Mild compression, around 1.4 to 1.9 times, is nearly free across all methods. The break only appears when you push past 3 times. Honest scope. First, graceful degradation has a limit. NVT pushed to 7.6 times flops also breaks, its noise falling below TOMI at only 2.6 times. The dichotomy is real but regime-bound. Second, the dimensional collapse mechanism is figure-only, no tabulated values, so it is read off a plot, not a table. Third, FPS is a single hardware point on one GPU. And on Cityscape's noise, prune then merge actually loses to CTS by a hair, so it is not strictly best on every single cell. The takeaway: token compression and structural pruning are not interchangeable. At high compression, merging tokens collapses the feature space while thinning the architecture degrades smoothly. Stack them, prune, then merge, and you get the best of both. But always check the real bottleneck: latency, not flops. Subscribe for the next paper breakdown.